Hello and welcome back to another IB Math speedrun with me, Vince. In this speedrun, we're going to be going over some trigonometric substitutions and integration, and also how to simplify some definite integrals using integration by substitution. So let's jump right in. So the first thing is, remember if we get the derivative of an inverse trigonometric function, it normally looks in the form 1 over, I guess it's a squared minus x squared. A over a squared minus x squared. So we can use this in reverse in integration. So if we have some integrand of the form 1 over the square root of a squared minus x squared, we want to use the substitution x is equal to a sine u. If we have one that's 1 over the square root of x squared minus a squared, we want to use the substitution x is equal to a secant u. Notice not cosine. And finally, if we have something like 1 over the square root of x squared plus a squared, we want to use the substitution x is equal to a tangent u. So yeah. And then there's one more important thing for definite integrals. If we do integration by substitution, say we have the expression 2x plus 1 squared, and we say between 2 and 1 dx. If we substitute u is equal to 2x plus 1, we also want to convert these definite integral limits. Of course, du over dx is equal to 2. So we have this is equal to, well, we need to substitute this limit into here. So this would be 5. The new limit is 5 and 3 of 1/2 u squared du. And so we can solve this directly. So now we get the 5 and 3 of 1/6 u cubed. And so this is simply equal to 125 over 6 minus 27 over 6. And so this will give this exact same answer as if we converted the limit, this resulting thing, back into x. So we can use that as a sort of shortcut. So with that being said, let's jump into some questions. So the first question, I guess we'll do the even ones, is we have to solve the definite integral of between 4 and 3 of x over 2 minus x squared dx. So we're going to use the substitution u is equal to 2 minus x. So du over dx is equal to -1. So we have the integral of negative 2 minus u over u squared du. Yeah. So this is equal to the integral of negative 4 over u squared minus 4 over u plus 1. Oh, and then we have to flip these all around again. So this is -4 plus 4 over u minus 1. No, where did all of it go? -4 again, plus 4 minus 1. So this is equal to du. And the boundaries are, we need to change these limits into 2 minus 4 is -2. 2 minus 3 is -1. So we actually flip these into -1 and -2. And so we get integral between -1 and -2 of 4u to the -1 plus 4 ln u minus u. So this will be equal to 4 times -1 to the -1, so that's -4 plus 4 ln -1 plus 1 minus 4 over 2, so this is plus 2 plus 4 ln negative 2 minus 2, so it's plus 1, plus 2. Oh, sorry, this would be minus 2, because minus, and then we have to minus again, so this would be minus 2. So if we combine all of this, we get negative 4 minus 2, negative 6 plus 3 is negative 3, plus 4 ln 2, I think. So, yeah, so this is simply ln 16. Oh, it's plus 3. Interesting. Maybe I've made a mistake with the limits. For u negative 1. Unless this is, oh wait, this might be negative. Yeah, this is negative for u negative 1. Oopsies. So yeah, it's ln 16 plus 3. Anyways, on to the next one. And the next question is the integral between 3 halves and 0 of 1 over the square root of 9 minus 4x squared dx. And so here we can use some trigonometric substitution. So in this case, we want to make the substitution that x is equal to, this is really equal to 9 over 4 technically. X is equal to, yeah, it should be 9 over 4, I think. So 3 halves, in other words, sine u. So we get dx over du is equal to 3 halves cosine u. So we can multiply this entire thing by 3 halves cosine u. So we get 3 halves and 0 of 3 halves cosine u over x is equal to 3 halves sine u. So we have 9 minus 3 sine u squared, 9 sine u squared. So this is equal to cosine squared u. Sorry, cosine u. So since we have cosine u in bottom and top, we can cross these out. So we simply end up with, oh, we have not converted the bounds. Oops. So we have, this is 1 is equal to sine u, so u is equal to pi over 2. And then 0 is equal to sine u, u is equal to 0. So this is fine bounds. And then so we have this integral over here. So we need to get pi over 2 and 0 of 3 halves u. So this should be 3 pi over 4. I don't know why it's not just 3 pi over 4, so I'm actually going to take 3 pi over 4. The book says pi over 4, and I'm not exactly sure. Why would that be? I'm not sure. So anyways, we get to go to the next one. And the next question involves this. So we have the limit between 1 and 2, 1 and 3 halves of 1 minus 2x times 1 plus x minus x squared all over 1 plus x minus x squared dx. So it's pretty obvious we have to substitute u is equal to 1 plus x minus x squared. So du over dx is equal to 1 minus 2x, which works out nicely. So we have the limit between 3 halves and 1. Oh, no, we do not have the limit between those two. We need to convert this limit. So we have the integral of u to the 1/2 over u. So this is u to the negative 1/2. Du. and we need to convert the bound. So 3 halves, 1 plus 3 halves minus 9 fourths is 1 plus 3 halves minus 9 over 4. It's equal to 1/4. And then 1 plus 1 minus 1 is equal to 1. So we have the integral between 1 and 1/4 of u to the 1/2. Sorry, you couldn't see that. And so this should be equal to 2 u to the 1/2, really. So this should be equal to 2 minus a large number. This is 2 times 1/4 to the 1/2, so 2 times 2. So this should be equal to 2, I think. Where are we? 6. Oh, that's weird. It's not equal to 2. 2u to the 1/2. 2 minus 1/4 to the 1/2 is equal to 1/2. Okay, so this should be 2 minus 1. Should be 1. The book says -1, which could be some minus sign miscalculation somewhere. But anyways, it is the same nevertheless. Okay, on to the next one. And the next one we have the limit between pi over 4 and 0 of secant squared x tan cubed x dx. This is a fun one. So what do we have here? We can say u is equal to tan x, and then du over dx is equal to secant squared x. So we have the limits of tan x, tan pi over 4 is 1, 0 of x cubed, u cubed, du. So this is equal to simply the limit between 1 and 0 of 1/4 u to the 4, which is equal to 1/4. And yeah, that's it. It's just 1/4. So yeah, that's correct. And then on to the next question. Okay, next question is we need to solve this limit between 2 and 0 of 3 to the x times root 3 to the x dx. So we have u is equal to 3 to the x, du over dx is equal to ln 3 times 3 to the x. So this will be equal to integral of 1 over ln 3 times u to the 1/2. So the limit is between 2 and 0, so 3 to the squared is 9, and 3 to the 0 is 1, so we need to get those limits. And so this will be equal to the limit between 9 and 1 of 2 over 3 ln 3 u to the 3/2. So this is equal to 54 over 3, so that would be, because 9 to the 3/2 is 27, 9, 18 over ln 3 minus 2 over 3 ln 3. So if we were to convert this, this would be 54 minus 2 is equal to 52 over 3 ln 3, I believe. Yeah, it's correct. So next question we have, given that the integral between 0 and pi over 3 sine kx cosine 3kx dx is equal to 3 over 16k, find k. And so this isn't too hard. So what we have here is we can substitute u is equal to cosine kx, so du over dx is equal to negative sine kx. So we have the integral between, oh sorry, negative k sine kx. So we have negative 1 over k times u cubed is equal to 3 over 16k. And to change the limits, cosine, so we have cosine pi over 3k, so k pi over 3, and cosine 0 is going to be 1. So if we integrate this, we get 1 and cosine k pi over 3 of, this will be 1 over 4k u to the 4 should be equal to 3 over 16k. So we have 1 over 4k minus 1 over 4k cosine k to the pi over 3 is equal to 3 over 16k. So if we subtract these two, this would be equal to 1 over 16k. It's equal to 1 over 4k cosine k pi over 3. So we have 1/4 is equal to cosine k pi over 3. What would this be? So we have k pi over 3 is equal to arc cosine 0.25. So this is around 1.318 radians. So k is equal to that times 3 over pi. So this should be around 1.26. Oh, this is cosine to the power of 4. Ooh. K pi over 3, so that's why, because so this is cosine to the power of 4. So we have 1/4 is equal to cosine to the power of 4 of k pi over 3. So this would be what? 1 over root 2 is equal to cosine k pi. Okay, and this makes much more sense, because then of course k must be equal to 4/3, because k pi over 3 must be equal to 1/4. Okay, cool. I mean pi over 4. So k is equal to 3/4. I mean, what am I doing? 3/4. Okay, and then on to the last question. So the last question is, show that e to the x plus e to the minus x is equal to e to the 2x plus 1 over e to the x, and use an appropriate substitution. Okay, so we can prove this is true, because this is equal to e to the 2x over e to the x plus 1 over e to the x. And so if we add them together, we get that. So we need to then solve this equation, negative ln root 3 and 0, and the bounds is 1 over e to the x plus e to the negative x dx is equal to negative pi over 12. So we need to prove this. So we know that this is then equal to e to the x over e to the 2x plus 1. So negative ln root 3, 0 of e to the x over e to the 2x plus 1 dx. And then an appropriate substitution would be I guess u is equal to e to the 2x plus 1. It's not the nicest substitution. Du over dx is equal to 2e to the 2x. So then we have square root, integral of negative ln root 3 and 0. Actually, no, we need to convert these bounds. So e to the 0 is 1 plus 1 is 2. E to the negative ln root 3 is negative root 3 plus 1. Wait, e to the 2 times negative ln root 3. So this is what? So ln 1 over root 3. 2 times ln 1 over root, 2 times ln 1 over root 3. So that's 2 times 1, so it's 1/3 plus 1. So we have 4/3. So let's just change these bounds to 2 and 4/3. And then we have 1 over 2 e to the x times u du. So now we need to convert this. We can say that 2 e to the x is equal to 2 e to the x is equal to e to the 2x plus 1 minus 1 times 2. 2 times the square root of that. So it's 2 times the square root of u minus 1. Oh, of course, wait, we could just... what am I doing? Oh, I'm so silly. We could just use trigonometric substitution. Okay. So we have e to the 2x plus 1, so this is going to be a tan substitution. So we want to use u is equal to the tangent of e to the 2x. No, so like, oh, please don't do that. So we have tangent of u is equal to e to the x. Yeah, okay, and then, so, yeah. So then, what is this? So, e to the x dx is equal to secant squared u du, and then secant squared u is also equal to e to the 2x plus 1. Yeah, because this is tan u, tangent squared u plus 1. So it's e to the 2x plus 1. Okay, so this is cool. So then we can do that this is equal to just actually nothing, technically. Yeah, because we need to multiply by the opposite of this. So this is simply, we need to convert the limits. So tan u is e to the x, so tan u is 1 over root 3. So that's root 3 over 3. Hold on, wait, no. Yeah, tan u is 1 over root 3 and 0. No. E to the 1, e to the 0, 1, tan u 1. Okay, so this is actually going to be pi over 6 and pi over 4 of just du, since there's nothing left, which is equal to pi over 4, pi over 6. Technically pi over 6, pi over 4. Pi over 6, pi over 4 of this, so just u. So this is equal to pi over 6 minus pi over 4, which is equal to pi over 12. Well, negative pi over 12, but then we absolute value, so it's equal to pi over 12. So yeah, that's all for these speedruns, for this speedrun, and I hope to see you in the next speedrun. So see you then.